Two. Fantastic. So my name is Dagmar Gromann, and I'm from the University of Vienna, and I've been working on knowledge representation and knowledge extraction, machine learning and AI, and all of this mostly from a very multilingual perspective. Now we know that the power of machine learning is omnipresent, and machine learning really has entered almost all of our everyday life, from healthcare to criminal justice, and of course also language resources and language services. And we've already heard a lot about this yesterday, that there are so many different architectures, from very simple perceptrons to really highly complicated transformers, graph neural networks, and so on. And with this whole plethora of different neural architectures, there are also a lot of pre-trained multilingual language models that we can use. So for instance, there's multilingual BART and just BART, machine translation models. There's BERT, which of course many of you know already or have used already. There's also multilingual BERT, and there are millions of variations of different BERT models, including Roberta. And then there's a more robust version of Roberta, which is XLMR, which is an extremely multilingual model. It's trained on 120 languages. You probably have heard about GPT-3, which is extremely successful at the moment. It's more of a commercial solution than the others, which are really freely available. For GPT-3, you have only a small proportion that you can use freely, and then you would have to get a paid account, but it's very powerful and it's been used in many different tasks. And many of these models are available on platforms such as Hugging Face, which probably many of you know already. Now, at the moment, many of us are using all of these models, but we are not at the end of their capabilities. We don't know exactly yet what they're all capable of. But what we do know is that they've been vastly successful in a very wide variety of natural language tasks. So if you look at the common challenges online from ACL, like Semival or something, you find so many different tasks, from natural language inference to joke explanation, which is also a very funny task, information extraction, that's closer to what we talk about here, such as relation extraction. But you also find something like text summarization or question answering as a task there. And very recently, the most media present task right now is generating images from text. Why is that? Because earlier this year, the AI system Midjourney submitted a painting generated by the AI to an art competition in Colorado State, and it actually won the competition. So that's how it got a lot of media traction. And I thought, since we are in Lithuania, let's try this on Lithuanian ideas. So I tried to generate a painting by a famous painter here, which according to Google pronunciation is called Čiurlionis. Please correct me. Okay. And the painting is called Fairy Tale Castle with full stops. So I just tried Fairy Tale Castle without punctuation and painting, and try to see what can we get from that. So Stable Diffusion by Stability AI thinks that is a very good fairy tale castle painting. We've heard yesterday already in Jorge's keynote, that was in a different land, that there's DALL-E that's vastly successful. It's also vastly successful on generating images from text. And it is a bit more of an abstract painting than the first one. DALL-E Mini, which is a small version of the huge model, you can freely test and try out yourself in this Crayon version. So Crayon provides like an online demo of DALL-E. You just put text and then it generates, for instance, this image. And for comparison, this is the actual painting. So I think human creativity is still a little bit higher. So this is what Čiurlionis thinks a fairy tale castle looks like. And if you compare it to the other two, it's a bit more creative in my view. Just realized I forgot to start the time. Of course, since we are very much into language, or most of us are very much into language, I thought it would be interesting to see how well these models do on different languages. Not sure I should try to pronounce that one. Is it Borkelli or Sruba? Sruba? Okay. So I tried what happens if you put this Lithuanian phrase into those models. Stable Diffusion thinks it's some kind of foresty garden, right? Something where you have some trees. DALL-E Mini thinks it's a person that has lived at the very onset of photography. So it's a very, very old photo. Do you know what it is? I mean, those of you who are not natives? It's a soup, yes, exactly. It is a soup, okay? So that clearly shows not multilingual yet. It's really very much focused on English. And as a matter of fact, when it gets multilingual, this task is so much more difficult to generate images from text, because what is prototypical in one language is not prototypical in another language. So if you look at, for instance, the concept of lunch, the next point on our agenda, if you type lunch into Google image search, you get something like this. I particularly like the one on the right corner, the metal tray, you know, which is really a canteen type lunch. If you type the same thing, the same word with the same meaning in another language, you get a very different idea of what a lunch might look like. Okay, so it's much more hearty food. And this is really true, that people associate different things with meaning and with language. So this is very tricky, no? Also for this task of generating images. Let's come back more to the topic of terminologies, okay? So we know one object might have one concept, but is it only one, or are there many concepts that can be associated with one object? Not just across languages, but also within a language. So what would you say this is? Pollination. Pollination? That is super interesting. Any other ideas? But what about the animal? It's a bee, okay. Let's already be a bit more specific than a bee. It's actually a bumblebee, which is a bit bigger than a bee. Slightly different animal. It can be a humblebee or a bumblebee with hyphen. This is just a general idea. Let's say we are into biology, then we want to know what is it specifically. It's not just any bumblebee, it's an apple bumblebee. It's a very specific species. Now, talking about species, what if you want to really classify it? Then it becomes a Bombus pomorum, which is basically Latin for apple bumblebee. But still, that's what you use if you do biological classifications and systematicity. If you're into agriculture, you say pollinator. It's an orchard pollinator, right? So very different perspectives on one and the same object. If you're into biodiversity, you might not even care what species it is. You might just care that it's actually an endangered species. So there are many, many different perspectives on how you can look at an object and describe it. So what do we do in terminology? We make it simple. We just say we focus on one domain. And by just focusing on one of those domains, we can also relate concepts in this domain. So let's take the example of biology. Let's say our bumblebee is a biological beast. So then it's an apple bumblebee and an Bombus pomorum. In that case, we can associate a German term to it because we know exactly what it is. So then it's an Obsthummel in German. And it makes it easier to relate it to other concepts. So we can say the hyponym of this concept is bumblebee. It's more general. If it was an agricultural terminology, we would have to say pollinator, maybe. We couldn't say bumblebee. So it really helps a lot to also construct this concept system if you restrict it to a specific domain. And then, of course, we can talk about its parts. So there's this suckling and feeding tube that they have, which is one part. It's called a proboscis, sorry, because we're still in biology, right? We don't just want to call it a tube. And of course, there are different types of relations we might use. So to give a bit more of a complete picture of possible terminological relations, we had the is-a relation, the generic one, the hyponymy. Then there's the partitive relation, parts and whole relation, but you can also have a lot of non-hierarchical relations, such as activity and actor, or you want to talk about where something or someone is from, origination. You might want to talk about cause and effect, ownership, or spatial relations where something is located, and so on. Then there are lexicosemantic relations, which you probably know, most of you know best. Hypernymy, which is very similar to is-at, so something is more general than something else, or something has parts, which is meronymy or meronyms in this lexicosemantic classification. And then you can have synonyms. In the case of terminology, these are just grouped by concept, and that's how you know they're synonyms or equivalent. And you can also have antonyms, opposites. Most of you, I think, here know this BATS, bigger analogy test set, because we've been trying to translate that to different languages. So many of you are very well familiar with these relations and the examples. Now, when it comes to neural approaches, I would like to give a brief overview of what's been going on there, how you can actually acquire relations. In order to talk about that, we first need to specify the task a bit more. There are many different versions of one and the same task. The very first version is you look at named entities. You really look at names, things you can assign a name to, which is people, organizations, monuments, and so on. In the sentence, Pablo Picasso invented Cubism, the names are Pablo Picasso and Cubism, right? And then the relation can be invent. And this is something that's done a lot in this kind of area. You just take the verb and then that's your relation. Sometimes you would disambiguate the relation and try to map it to a typology, but frequently it's really just taken. So the very first approach in this area is open information extraction. That's a very long-standing approach. It has a very long history. And it usually is done as a pipeline approach. You start by trying to recognize the entities in the sentence, then you try to extract the relation. Sometimes people do entity typing, which means once you know Pablo is a person, Pablo is a named entity, you want to also find out that it's a person. That's entity typing. And you want to say that Cubism is a type of art style. So this is something that people do as well. And then at the end, you somehow need to represent the data you have. Yeah, you can just put it in a text file line by line, but ideally you would have some proper triplet or knowledge graph representation at the end. Not always, but frequently people do. The second type of category here for named entity and relation extraction is supervised relation extraction. That can be with a pre-trained model or even without. If it's without, you need even more training data. The interesting part here is that many of these supervised approaches do entity and relation extraction in one go. They try to not do it as a pipeline, not use different models, but really do it as one task. And frequently this is treated as some kind of triplet classification with many different variations. But somehow, yeah, this has been very successful. Problem here, if you want to do it in Lithuanian, where do you get the data from, for instance? So there are not that many data sets for this. Finally, there's a very famous zero-shot and few-shot learning or approach. This is really very much based on fine-tuning pre-trained models. And zero-shot means you have absolutely no training data. So you train a model on some languages, and then you just expect it to know the same task in a different language, which works actually for this kind of task, not so bad. I will show you later. You can treat both the zero-shot, where you have zero examples, or few-shot, where you have very few examples, for instance, as a question answering task. This is something that's been done a lot. So you ask a question, and then the answer is either the one of the entities in the relation or the relation itself. In order to do that, people have been using question answering models, so models trained on the task of question answering, or models trained on a task of machine reading comprehension. That has worked best so far. Now, if you want to make the task a bit more difficult and a bit broader, you go away from these named entities, but you really want to extract domain-specific words and terms in a text, and then get the relations between these. So it's a bit more general than just names. In the text, motor vehicle refers to any power-driven vehicle, which is normally used for carrying persons or goods by road or for drawing. And then you have the specification such vehicles include those used for, and then that's a synonym of the one before, carriage of persons or goods. So what you want to find out is that a motor vehicle is a synonym to the power-driven vehicle. The more generic relation is a vehicle, and it can be used for carrying persons or goods, which is synonymous to carriage of persons or goods. That didn't fit on the slides anymore. So you have 2 relations already that you can extract and 5 terms, basically. If you want to do that with pre-trained neural language models, there's also a simplification of that task, which is you already give it the terms and then just say, tell me the relation. So, for instance, you have a context where you say recessions are caused by inflation, and you tell the model already as one option that recession and inflation are the two terms you want to look at. And then the model is supposed to tell you that the causal relation actually goes from inflation to recession, which is also important which direction this relation takes. So one method here is relation induction. You utilize existing data sets. Problem with existing analogy data sets, as we know, is it's usually just pairs of words. You don't have context, and for these kind of methods you need context, which is a sentence in which these words are used and related to each other. So what do? You generate this context. How do you generate it? You can just verbalize patterns, for instance. That's something that's done a lot. Or you just search for the context. People have been using Wikipedia as a corpus because it's multilingual, and you just search for sentences in which these 2 words occur. How do you then query the model? One way is you say you mask something. Masking is always this closed test type. So you just omit one word from the sentence and expect the model to predict it. This is the classical masking task. Or you can do question answering again. The more recent one that's been mentioned along this conference already is natural language prompting. That's like a hype right now in all natural language tasks. You try to find the ideal prompt. So what's a prompt? It's not just giving the model a context sentence, but it's giving it a natural language description of the task itself. You try to somehow describe the task in natural language to the model. And it has been shown that this is more successful than just giving it the context and fine-tuning it or training it on some examples. If you use prompts and you find the correct prompt for a task, it's very successful. So prompt designing is a new research direction right now. How can you automatically generate those prompts, describe the task you want to do? In this case, it's give us some kind of relation. How can we prompt this? For instance, we can give it a sentence like Steve Jobs left Apple in 1985. In this sentence, we want the model to realize that there's a relation between Steve Jobs and Apple, and at least it's some kind of employee relation. And then we can add a prompt to it, which says Steve Jobs is the of Apple. What would you say? I mean, you know it probably anyhow, right? CEO, leader. So there's some options here, right? We want the model to at least come up with one. How can you do this prompting? Like, do you really want to sit down and generate that for each sentence yourself? No, you want to auto-generate it. So people have really put a lot of research into generating templates automatically using neural language models again to then prompt other neural language models. So that's like the way it is right now. More interestingly, people have started using ontologies and linked data resources for this. So this is something where you can auto-generate prompts using knowledge that's out there already. The final one is more of a fun task for robustness of the models. Do you know adversarial training, where you try to confuse the model that you've trained? Yeah. So here, for instance, they humanly generated these adversarial examples. It's really the purpose to see how sure is the model about its predictions. How sure is it about the knowledge it has? If you give it a very hard, a very confusing input, what does the trained and finalized model tell you? So for instance, a building dedicated to this man was the site of the I have a dream speech. What would you say? Lincoln, yes, it's, yeah, the Lincoln Memorial. So the person is, see, that's exactly what the model said. The person is Abraham Lincoln, because the question is a building dedicated to this man. It's the Lincoln Memorial, so it's Abraham Lincoln is the correct answer. So it's a very confusing example. Sometimes even for humans, you might say Martin Luther King in the first instance. And that's exactly what the model said in this case. It would say Martin Luther King because it says, I have a dream. But the question here actually is, who is the building dedicated to? And that's Abraham Lincoln. So you see it's confusing examples, and there you can test the knowledge that's inside the models and really how robust your trained model is. So that's kind of a fun and interesting way of looking at it. To look into this ontology-based prompting just a little bit more, let's say we have the sentence, Bill Gates is the co-founder of Microsoft. We can query an ontology and we can get information such as Bill Gates is an entrepreneur, which in turn is a person, or who in turn is a person. We can say Microsoft is a company, that in turn is an organization, and then lots of information around these concepts. And the way that this has been used in prompting is that you provide some of this information to the input, you attach it, you add it to the input. So you don't just have the context sentence and the entities, but you actually provide some more information. Of course, you might not want to say leader of, because that's what you want to get in the end. You want to predict the model to predict that it's leader of. So you just give it certain contexts and not all of it, such as that it's a person, an organization, and so on. Okay, so this is the idea here. If you want to make the task more difficult, you don't have terms. You want to extract everything from scratch. This is something that we did in our project. So it was called Extracting Terminological Concept Systems from Natural Language Text to TCS. It's quite a hard task because you first need to extract the terms and then you need to extract the relations. So what we did there was a rather simple fine-tuning and pipeline approach, but it was the first of its kind because this has only been done for named entities and not for terms. So first we would have to find out which language it is, because it's a highly multilingual model that's been trained on German and English, but has been tested on French, Russian, Portuguese, Italian, Hungarian, Japanese, Chinese, Finnish, and yeah, that's it, I think. But the model itself can speak or has been trained on 100 languages. So feel free to try this out. It's freely available online on the European Language Grid in your language, and let us know. This is zero-shot transfer learning, right? Which people have tried, and sometimes it works actually surprisingly well. Okay, and then we extracted the terms, and afterwards the relations. The problem is that many relations are not on sentence level. You actually need to look at the whole document, because acronyms, for instance, are scattered all over the text. It's not just in one sentence. So you really want to get some of the relations on document level. So in the end, you need to decide which relation is more important. Do you want to keep all the relations from sentence and document, or do you need to filter a little bit? This is what we tried to do in the end. Just briefly, how did we do that? We tried many different ways, and how you actually fine-tune a model makes a huge difference. The first one was sequence classification. Sequence classification means you have to create all possible sequences out of a sentence. So you have to try we. Is we a term or not? No. Okay. We meta-analyzed. Not a term. We meta-analyzed mortality. Still not a term, because we is not a term. And then you have to do that for all combinations of all lengths of all sentences. You can imagine this model never stops. I mean, it does. The accuracy was okay, but it actually took so much longer than the token classification, and the results were worse. So the second thing we tried was give it a sentence and let it classify each individual token in the sentence. Tell me, is this token, in this case, tokens are words or punctuation. Is this token a term or not? If it is a term, is the next term, a next word, a continuation of the term or not? So BT is term, and then T means continuation. So random effect is the beginning, and model still is the same term. It's a continuation. This worked best. We also tried neural machine translation, where you really just give the model a sentence and you can train it to output all the terms in the sentence. That actually worked quite well, especially for long multi-word terms. If you have like 5 or 6 words in a term, which is very common in highly specialized domains, then this worked best. Problem is, it also gets creative. It invented terms in French that weren't even in the text, okay, based on the English. So the reliability is a bit of an issue. And the models are so much bigger than XLMR. And we, in our project, were obliged to produce software that can be used online on the ELG. So this was too big, basically. But we didn't stop with the neural machine translation models, because it actually turns out that you can use them to do term and relation extraction at the same time in one go with one model. That actually worked quite well. But the model is very big, and the inference time on the hardware that they provided for us was 40 minutes per query, because the hardware wasn't very good. So you need really a strong server, a strong system behind it that it works. So in the end, it became the XLMR model again, fine-tuned for relation extraction. It gets the terms we extracted in the first step, and then it predicts the relation. It gets the terms and the sentences, of course. So let's just summarize briefly what ways have we discussed now to do relation extraction. Relation classification with or without context. You get some entities or terms, you try to get the relation from a typology. Question answering, what type of fruit is a Granny Smith? Apple, hopefully. Inducing, you mask something and you hope the model will give you the target entity. Discrete prompting, I'm emphasizing the discrete here because there's also a continuous prompting. Discrete means natural language. You add something to the input. The newest trend now is to really try to manipulate the vector space in order to input those prompts. That's continuous prompting. It's a whole different animal. That would be a talk on its own, I think. So Steve Jobs left Apple, and then you have a second sentence that represents the description of what you want the model to do. Adversarial testing, difficult examples. Maybe many, many more. These are the examples that I selected that I found very useful. Maybe there are many, many more already today. So where did the linked data go in all of this? Well, first of all, many data sets are generated with linked data. So you really try to generate natural language contexts and relations, building on Wiktionary, Wikipedia, and DBinary connections. That's something that they did with the T-Rex dataset, for instance. You can verbalize multilingual context from linked language data. That's been done at the Jerusalem workshop, a paper by Lucia Bitarch and Jorge Gracia and colleagues. So you can really try to generate natural language versions of the triplets you have. You can do knowledge-enhanced learning. We've heard quite a lot about different bird models. There are also bird models that have been trained with triplets or graphs. So K-bird or Coke-bird, for instance. Of course, you also have all these graph convolutional networks that you can use in this regard. Or you can auto-generate prompts using linked data. So you can try to come up with the best description of the task or the best prompts using already existing structured knowledge. And of course, very importantly, you can represent the results, the triplets, and also the knowledge graphs that you produce in a linked data format. And I think it's on us or our task to come up with many, many more. So if you have any ideas, please feel free. You know, I think this is interesting. We've heard about the combination of structured knowledge and neural approaches, so sub-symbolic and symbolic AI, which is really still a big field. And this goes into that direction. And I think there's much more that we can do there, maybe. This is just like a first idea. So to conclude, I think I'm already running a little bit late, but I'll be done soon. I really like this quote by Warren Buffett: "Bad terminology is the enemy of good thinking." So let's make sure whatever we create, extract, or acquire is actually good terminology. In that regard, I have some more hints or some more things we might want to check for. Pitfalls. So bias is a huge problem. Many of these language models are extremely biased, which we found in our project and during our training. So if you ask the model, what's the relation between white and criminal? It says absolutely none. They have nothing to do with each other. If you ask it, what's the relation between black and criminal? It tells you it's a hyponym. Of course, they're totally related, which is not okay. So we really need to test and check for those kind of biases in the models, especially when we use them with zero-shot learning across languages, but even if you just use it with fine-tuning. Another pitfall, of course, is multilingual models used for multilingual tasks. There are not many data sets that you can test and evaluate on. There are very few approaches that try to do that, and there are even fewer approaches that really evaluate the zero-shot and few-shot results. We also have to, put that on our plate, because we also tested only on 10 of the 120 languages that the model is supposed to be able to do. So it's very hard to test on all the languages. And finally, evaluation. It's been discussed at this conference, and it is a problem. In my view, it is a problem. These kind of tasks still rely on the idea that there is exactly one answer and not more. And I think in many cases, there's way more than one answer for this task. There are synonyms that might be correct in the same relation. There's polysemy that you need to consider. And if you just put a little bit of an alteration on the input, the model gives you a completely different output. So this is really something where the evaluation needs to be more than just saying it's correct or not, or it retrieved enough examples or not. So if you have any ideas for a better evaluation, especially if you look at relations on document level, it becomes more difficult. So if you have any ideas, please feel free to let me know. I'm very interested. So now the very last slide. There are many methods that we can use, that we can try out, that we can test. But do we actually test the knowledge, the common sense knowledge and the linguistic knowledge inside those models with these kind of methods? What is the true linguistic knowledge and the true common sense knowledge? It's very hard. Maybe we cannot know exactly how much the model knows, but we can definitely check for those pitfalls such as bias. We can definitely check for the robustness of the model, give it really difficult examples and see how well it actually is able to handle those. So the open issues are, of course, robustness. How do you test it? It's been shown a lot that if you just put a synonym in a relation or in a context or whatever, it changes the model completely, sometimes even breaks it. If you just alterate the input by adding an also or a to in the context sentence, it can already break the model. These are the things you should try, but it should be done more systematically. Like, how can you systematically test robustness of the relation extraction models, really? Maybe we should go beyond fine-tuning. So the first approach to do that is this continuous prompting, where we really try to manipulate the vector space. More on the LLOD side, something that's a community issue right now is how do you actually represent terminologies? It's an ongoing discussion. There's not yet the final and perfect solution. This is how terminologies are represented as linguistic linked data. If you're interested in that, please get in touch with the Ontolex community, basically, because there are many people in that community working on this and very interested. Or get in touch with me, I'm also very interested in that. And of course, multilingual and cross-lingual approaches are a big thing. That's why we are translating the BATS dataset and having a lot of fun since a couple of months. Because it's important to get more multilingual and highly multilingual approaches out there. So thank you very much for listening. And if you have any answers or questions for me, I'm very happy.
Did you investigate graph learning, like graph-to-back and other models that will predict relations? something learned from the graph?
We did not, for the simple reason that all of these approaches so far are really focused on named entities. So all these graph completion and graph learning approaches only work and are only tested and are only available for named entities. We would still have to extract the terms and the relations. So it didn't make the task easier. So no, we did not. Any other comments, answers, questions, complaints?
My question is more from social humanistic approach. Because one thing is that that prejudices and so my observation is that the biases and prejudices are embedded in cultures and life. And when we train the models, so probably the machines simply identify them. And so people carry these prejudices, sometimes even subconsciously.
Yeah, absolutely.
Especially concerning gender.
So yeah, that's very true. We all of these models are currently trained on the data that's out there. And if you look at Twitter, bots have been trained on tweets and turned into neo-Nazi within 2 hours. So depending on which data you use, even if you use all the data out there in the web, it's still going to be biased for 100% sure. The problem is if you de-bias in one direction, let's say gender, then suddenly you have a massive racial bias. So it's so hard to test against all biases. But yes, it is a problem of how the models are trained. So this is maybe also something that we might want to consider. You know, is there a better way of training these models than using massive data that's out there and radically biased?
Well, maybe it's also related to my first question. In all these works, and almost all the work that is done, we are always trying to ask the model what they know about language or concepts, and they only have been trained on what we say. And we assume that by just learning what words should be there in this sentence, the model learns something that is meaningful.
Mm-hmm.
So you mentioned prompting graphing, which is just a way to extract information from the model and try to understand what he learned. But what I want to say is that we always learn on the text. We always learn from the stream, and it generalizes because we have so many streams that we don't even know what learning is. Is it only a kind of artificial associative memory, or does it learn something which has really some meaning? And the bias is part of it, because there is overrepresentation of some text. We studied the journalistic text, very serious ones, and we found out that it gives speech to men at about a rate of 60 to 70%, even in mainstream, and it's continuous. So there is a bias, a very huge bias in this text. And maybe in the graphs, in the ontology we have, in the even the ontologies or only Wikipedia extracted ontologies, such biases are not present. And maybe it would be interesting to mix both approaches. For the moment, we do not have any model that will be able to take texts and graphs and try to learn from both.
There's some, but yeah, it's not exactly working on the same rate as the supervised ones, yeah.
Yeah, and for LLOD, maybe it's one of the directions you should take,
Yes.
because we are dealing with grass.
Yeah, I totally agree. The combination and or, you know.
I think there's so much more bias because all data sets are biased. So how can you expect models to be unbiased from biased data? Unless you want to doctor the models, which we don't want to do.
Well, yes, no, that's something that people do, but the problem is if you do, you might create a new bias. Yeah.
But then models are not true reflection of what we are and how we speak.
Yeah.
Either we want one or the other. Do we want to have an idealistic word with no biases? Or machine learning biases are taken from people? This is what we are.
Yes, but I still don't want to.
The social biases are there. Of course, we can use it to make the world.
But you cannot just accept the biases of the majority, and I mean you can accept the bias of the majority, but the problem is if you take this perspective, propagating bias is something that's a serious research issue. And if we just simply take that perspective and say, okay, it's fine to have the relation hypernymy from black to criminal, we are actively propagating bias, which is something that I personally am not willing to do.
Of course, and even bias are ground to when we are, in which culture we are. In some, at some point in time, these bias will not be a problem at all. Now it is. But the problem is what we do with it. If your purpose is to observe, then having a bias is a very good thing because you want to observe it and to deal with it somehow. But 90% of the purposes of the usage of this model is not to observe, but to decide, to propose, to select. And these biases are just huge. If you want to just, let's say, just put some curricula in the machine and let the machine extract the best person for this job, then you will get only men. Just because they train on a very biased data set, which is, well, who are the person in computer science companies? So the model is not stupid. You know that, okay, 80% are men, so this is the most critical feature that let me decide if I can or not.
What did you say about the speaking bias beforehand? There was 60% men. Do you like to pass the microphone?
We have this, we have a portal where we can observe day by day how it evolves, and it's the best is 60 to 40. Most of the time it's around 70.
I think there's another question up there. Milan.
So I just wanted to comment that in our keynotes is 50.
Thank you. You mentioned evaluations, and if I understood correctly, you were suggesting that there is a listening impact. So when looking for such perfect model, is it a model? Are these models maybe in some way listening to this bias thing? But is the search for one perfect thing, or actually there are various possibilities? And then we would get different answers. And if I may also refer to this questions and answers that you have here, in computer science, we refer to question answer. In the other part is the answer question. This is the womb of each answer. There is a question which takes us on. So do you think it's connected, in your opinion? Is there a model, or various possible models.
I mean, the evaluation is on the task usually, irrespective of which model you use. So to answer the first question, I think that there is more than one answer and evaluations should correspond. We try to account for this by trying to really detect synonyms. So we had a gold standard of what answer we expected, but then the model provided a slightly different one, like a shorter term or a term with a morphosyntactic variation and so on. We tried to catch these. We tried a lot of things. It's not easy. So that's why I think we should work on evaluation a lot more. The second question I didn't understand. What exactly was the question about answer questioning?
It wasn't a question, it was just a comment about that.
Okay.
We are looking at question answering. We want answers all the time. But actually, the moment that we have an answer, there's a new question that comes up. So it's a kind of an ever-growing process.
I mean, generating questions for the answers would be a lot easier because you have way more freedom. You can just, if you give a model Steve Jobs, you can just generate a numerous, range of questions. So I don't think that that's a way to go. Yeah. The task is too easy.
Thank you, Dagmar, and we can continue the discussion in an informal way during lunch because we are exceeding the time. So, if anybody wants to comment or then during the lunch. Okay, thank you.
Well, since you're not recording, you cannot stop it, right? Because you didn't have permission to record, right? Oh, no, now you do have permission, so I hope your colleague did record because I didn't push it in the middle of the talk. You have to ask. If not, it's
Because I told her that she should report for an hour. So
but she gave you permission now.
Ah, okay.
So let's see whether she recorded or not. It is recording though, yes, it's still recording.
Aš sustabdysiu. Tu palauk dabar.
Aha, baigti yra.